So boleh nampak tak slide yang saya sharekan? Can you see my slide? AC meters.
Boleh sir.
Boleh sir, boleh.
Okay. Okay, right class. So let's start our lecture for today. So today we go for the chapter 3 for the AC meters. Okay. Before that, let's go for the chapter 1 first. Okay, chapter 1 first because of the calibrating for the analog instrument. So on the chapter 2 we are done for the DC meters. Okay, we on the DC DC meter we have the voltmeter and DC ammeter lah. So that's why we have to know how to calibrate the this DC voltmeter and DC ammeter. This is continue for the chapter 1 because chapter 1 I just skip this one because first we focus on the DC meter, then we go for the calibration lah. Alright. So before we go for the chapter 3, so let's continue on chapter 1 on the calibrating analog instruments. Okay. So you can see this okay. So this is a DC voltmeter. How to calibrate? We just put okay. This is you can see this one. Okay. So this is our voltmeter for test. Under test, this is volt untuk ada test, and this is our standard instrument. So normally standard instrument we use the multimeter, digital multimeter lah. Okay, to compare the result between the voltmeter under test and the standard instrument lah. Okay, based on the digital multimeter. Okay, so to test the voltmeter reading V, okay, this one for this one. So we compare to the voltage reading obtained with the standard instrument lah. Alright, so the rheostat here. Function rheostat to limit the current lah. Okay, to limit the current flow to this circuit. Okay, that is how we calibrate our voltmeter lah. We put voltmeter under this one, under test here. Okay, and then we measure this one. So as you know, the voltage in parallel will be same lah. Okay, so that's why voltage here, okay, will be same with this one this R and also this one lah. Okay, that's why we put here because voltage in parallel will be same. Okay, that's why we just compare this voltmeter and on this one lah. Okay, so this one how to calibrate the voltmeter lah. Okay, right, so you have to check double check is it correct or not. Okay, follow the standard instrument or not so voltmeter for our voltmeter for under test this one. Okay, this is how calibrate the DC voltmeter lah. Okay, next how to calibrate the DC ammeter. Okay, DC ammeter. Okay, so you can see this one so we put DC ammeter series series because we want to measure the current okay, we have to put in series. Okay, alright, so this is our voltmeter lah. Okay, standard voltmeter. Okay, and then the calibrate using the standard resistor here. Okay, RS here. And then standard voltmeter as the figure 6.2 lah, this one This is for calibrating DC ammeter. Okay, so this is how to calibrate our DC voltmeter and DC ammeter lah. Right, so before I go for the chapter 3, so maybe we just do some revision because after I discuss with our coordinator for this subject, so you're from manufacturing, so suppose maybe we just refresh what for the basic of electrical lah. Okay, share this one first. Hello, boleh dengar tak?
Boleh doktor.
Okay, alright. So, sorry.
Boleh.
Boleh. Okay. So we open. Okay, so just okay. Okay. So let refresh. So on the basic electrical lah. So as you know, so this is just a refresh for the electrical basic. Okay. So this is Ohm's law. I think most of you know this one. So this is a voltage. Okay. So this is current and this is resistor. Right. So this is we call the Ohm's law. Right. From this Ohm's law we can derive lah. So for example we can get the current using this formula, this Ohm's law. Okay, V over R, or we want to calculate the R, we can also using this formula V over I. Okay, so it's come from this one lah. Okay, so this is basic Ohm's law. So another one that you have to remember is the P power. To calculate the power equals to I V, right? So this is voltage, this is current. Okay, to calculate the power, the equation for the power is the voltage multiplied by current. Okay, so for example, we can calculate this one. Okay, V over R. Okay, then equals to V power of 2 over R. Okay, so another question to calculate the power, or we can put as the I R divided by I. Okay, equals to I power of 2 multiplied by R. Okay, so this is a basic, basics of calculate the power. Okay, you can use this formula or this formula or this formula, depends on the value given lah. Okay, so this is basics that you have to remember. The Ohm's law, V equal to Ri. Okay, IR. So from this one you can derive to get the current or to get the resistor here using this formula, Ohm's law. Okay, right, clear this one, so this just basic basic for article that you have to remember this one lah. Right, for example, okay, next the basic is the, okay, for example, for the resistor lah, this just a basic for article. For example, if we have the resistors, okay, resistor in series, for example, R1, R2, R3, okay, and so on. Okay, so this can be equivalent to so on, RT, we call the R total lah. Okay, so resistor in series actually you can add lah. Okay, so RT equals to R1 plus R2 plus R3 lah. Okay, this is basic. So the resistor in series you can add. Okay, you can add lah. Alright, so for example, resistor in parallel. Okay, for example, we have resistor in parallel. Okay, this one R1, R2, and R3. Okay, the formula to calculate the resistor in parallel like this, R3 equals to, okay, 1 over R1 plus 1 over R2 plus 1 over R3. Okay, that is formula lah to calculate, and then you can simplify this one lah. Simplify to get this one lah. So R1, R2, R3. Okay, so this one R2, R3 plus R1, R3 plus R1, R2. Okay, and then okay, so this one, okay, we can this one. Okay, R equals to R1, R2, R3 divided by R2, R3 plus R1, R2, sorry, R3 plus R2, R3 so the R1, R2. Okay, that is formula to calculate the resistor in parallel lah. Okay, so that is some basics, okay, for article. And then another example, if we have current here, for example, we have current I here. Actually, current in series will be same lah. So current here will be I. So you have to remember this one. So current in series will be same. Okay, that's why current flow here will be same with current flow here. Okay, for example, this we can put as the 1 milliampere. So current here should be 1 milliampere. Okay, yes, this is basic for electrical. Okay, but for the voltage will be different lah. Okay, voltage will be different for the series. The voltage will be same with the parallel lah. For example, we have here V1, V2, V3. Yeah, that means voltage in parallel will be same lah. So that's why V1, V2, V3, okay, will be same. Okay, that is simple basics. Okay, basic of electrical. Okay, clear this one guys, this is the basic lah, so that you have to remember so this is basic political. Maybe some of you not remember, so just I refresh again for the basic of electrical. Okay, boleh Can?
Boleh sir, boleh.
Boleh sir.
Alright, so this is some revision revision on the basic electrical that you have to remember So the important one is the Ohm's law that you have to remember. From Ohm's law you can get this equation and also the power Okay, the power. And then make sure you have to remember this one Current in series will be same. Okay, voltage in parallel will be same. Okay, for example, voltage here 10 volt. So that means automatically we know voltage V2 and V3 will be 10 volt equals. Okay, voltage in parallel is the same. Okay, that is the basic electricals that you have to remember lah. So current within series, for example, we have the electrical circuit here. Okay, so for example, this is 10 volt. Okay, this is R1, 1K. For example, this is R2, 1K. Okay, that means to get the current, okay, that's why first you have to use this formula lah. V equal to R. R is the R total. So R in series just plus 1K plus 1K. Okay, volt. So our voltage will be 10 volt lah. So that is how to calculate the current. So the current here and current here will be same lah. So for example, you got the current here, and then to calculate the voltage for V1, okay, so this is okay, so this current using this formula lah, okay, current, you get the current, okay, and then multiply by R1 lah, 1K. So similar like this one lah, I, okay, and calculate the multiply by R, okay, to get the voltage here. Okay, but this is not same So for example, this connection, okay, alright, so voltage here, so will be same with voltage this one plus this one lah. Alright, so that's why we can get the voltage, okay, voltage in parallel lah. Okay, so this is some basic basic electrical. So let's go for the chapter 3 lah. Okay, so I hope that you can remember this one lah. So this is some basic electrical analysis. Okay, for example, to calculate the voltage, to calculate the power, to calculate the current and resistor. Okay, so let's start our chapter 3 Okay. Can you see the chapter 3 AC meters? Boleh nampak tak guys AC meters?
Nampak.
Okay, boleh So let's start our lecture for chapter 3 for the AC meters. Okay, so the chapter 2 will be DC meters. So now we go for the AC. AC is the alternating current lah. Arus ulang alik So in Malay we call the arus ulang alik lah. Okay, so the objective of this topic is to first is list 5 principal meter movement and application for each. Okay, So on the AC meter, we have the, so for example, we have the electrodynamometer. Okay, so ion vent, thermocouples, electrostatics, they are ensemble lah. They are ensembles. Okay, that is the meter movement that we can use for measure the alternating current. Alternating current. Okay, and then second objective is describe the purpose and operation of the diodes in half wave rectifier circuit and full wave rectifier circuit lah. So before you go for what is the half wave rectifier and full wave rectifier, so you have to know what is the rectifier. Okay, so the rectifier is to convert from AC to DC. That means the function of, okay, sorry. So the function of rectifier is to convert from AC alternating current to DC lah, to direct current. So that is the function of rectifier. Okay, you have to remember this one. The function of rectifier convert from AC to DC lah, convert from alternating current to direct current. Okay, and then third objective is describe the purpose of the second diode in half wave rectifier, which is often used in the rectifier circuits. Okay, and then list 5 application for electrodynamometer movement. And then last but not least is the list of the typical frequency range of the ion vent meter movement. Okay, so this is some objective for the chapter 3 for AC meters. Alright, so this is a electric AC electric signal lah, that I think this is basic lah. Okay, you can see this one. This is a sine wave lah. Okay, this is we call the sine wave response lah. Okay, or electrical signal. Okay, so first you have to know root mean square RMS value. Okay, for value of AC voltage is continually change from 0 to up to positive peaks. Okay, this one positive peak. You can see on the figure here. Alright, through 0 to the negative peaks, back to the 0 again. Okay, so this is we call the sinusoidal lah. Okay, so from this one go for the peak, vote for the positive value, and then go for 0, then go for the negative. Okay, this is negative peak value lah. Okay, so negative peak here, peak it will be same. For example, here is 240, this one also 240 lah, right? Okay, so clearly for the most of the time it is less than the peak voltage. Okay, so this is not good to measure the of its real effect. Instead we use the root mean square voltage lah, so which is 0.7 of the peak voltage. Okay, so this is formula for calculate the RMS. Okay, so formula for calculate the RMS equals to V peaks over square root of 2. Okay, this is formula for calculate the V peak lah. Calculate the VRMS. Okay, V peaks but divide by square root of 2 equals to, that means the square root of 2 equals to 0.7 lah. Okay, 0.7 multiplied by V peaks. Okay, alright. So this is formula. This is formula to calculate the VRMS. Okay, for example, if we have for example, our RMS voltage is 240. Okay, that normal lah for electrical, machine electrical is 240. That is for VRMS. Okay, and then you have to calculate the V peaks. Okay, that means V peaks you have to multiply lah. Okay, 0.7. Okay, this means okay 250 divided by 0.7 lah. So the voltage V peak we can get 340 something. Okay, 40 something for the V peak here. Okay, actually this equation also apply to the current lah. So the current will be same. Okay, that is formula to calculate the VRMS or calculate the V peak lah, based on this formula. So the formula for VRMS, okay, equals to 0.7 multiplied by V peaks. Okay. Okay, so you can see this one. So the RMS value is the effective value of the varying voltage or current, alright, is equivalent to steady state steady DC constant value, which is the give the same effect lah. Alright, for example, you can see this one. For example, the lamp connected to 5 volt RMS AC. That means equivalent to 5 volt DC supply. Okay, you have to remember this one. So 5 volts RMS, okay, AC is equivalent to 5 volt 6 volts DC supply, equivalent lah. Okay, so for example, if you connect to the connect to the 6 volts peaks, okay, 6 peaks, that means it's equivalent to 4.2 lah. It's not same. Okay, so the DC voltage is the same with the voltage in the RMS. Okay, so you can see this one. So 6 voltage RMS equivalent to 6 voltage DC. But if you connect to the 6 voltage peak, okay, peak, that means our equivalence to 4.2 DC lah, 4.2 DC. So that's why our lamp is not bright lah, okay, because of the DC. Okay, DC current will be 4.2. Okay, compare then if you connect to 6 volt, okay, RMS, okay, similar like 6 volt DC supply lah. Okay, that's the difference. So that's why you have to remember. Normally, so if not given, okay, for example, okay, so the question is not given, is state, okay, given state that this is a okay peak or RMS, so automatically you have to know. So this is RMS, okay. The standard is the RMS. The given, for example, 240 is the RMS value. For example, it's Malaysia. Malaysia, our supply is 240. So 240 is our RMS value. Okay, that's you have to remember lah. Okay. And then you have to calculate the voltage peak lah. So that we calculate the voltage peak, maybe something 300 something lah, 300 something. Okay, the givens, okay, the given supply here is the normally is the RMS. Okay, normally is the RMS. If not stated lah, it's not stated in the question or in the books. Okay, that's automatically you have to remember this is the RMS value. Okay, so it's stated, for example, okay, this is 6 volt peak. Okay, that means this is a voltage peak lah. Okay, if not stated, so connected to the 6 volts, okay, AC supply. So not given peak or RMS. So automatically you have to do assumption. Okay, this 6 volt is the RMS. Okay, this is 6 volt is the RMS value. All right. So next, you can see this one. So we cannot use the average voltage. So because if you use the average voltage, so will be zero. Will be zero because you can see this is a sine wave. Okay, sine wave. Okay, so if you average this one, okay, so automatically our voltage will be zero. That's why for AC we cannot use the average. Okay, we cannot use the average. If we use the average value, so automatically the answer will be zero. Because this one, this sine positive sine wave with minus with negative sine wave, automatically the average is zero. So that's why for AC we have to use the RMS voltage lah, not using the average. Okay. So what do AC meter show? So it's the RMS or peaks. Okay, that I mentioned to you. So AC voltmeter ammeter show the RMS value. Okay, that I mentioned to you. So using the RMS value, if it's not given, so automatically you have to remember. So this is RMS value. Okay, so the DC meter also show the RMS value when connected to the varying DC, providing the DC is the varying quickly. Okay, that's why also DC also they use the RMS value lah. Okay. Okay, so this that I mentioned to you. Okay, for example, here, alright. So if, for example, the UK main supply is 230 volts AC, that means this is 230 is the RMS lah, RMS. Okay, similar like Malaysia, similar like Malaysia 240 AC supply. That means our value is the RMS value lah. Okay, so you can calculate the peak voltage lah. So the peak voltage of this RMS is the 320 volt, for example, 340 volt. 320 volt lah. Okay, that is the voltage peak lah. Normally, if not given, so that I mentioned to you, just so this value is the RMS value. Okay, you have to remember lah. So this is a RMS value lah. Okay, and then for example, like Malaysia that I mentioned to you, so our supply in our house is the 240. So 240 is our RMS value, RMS value, root mean square value, alright. Okay, so this is a formula, okay, formula for calculate the RMS value actually in the electrical signal. Okay, so RMS value actually like this the equation from pi to, okay, pi that means 180 to 0. Okay, this is a sine wave, this is sine wave signal. Okay, so Vm sine, okay, omega t power of 2 d apa dw d d dt, okay, dwt, okay, equals to automatically when we derive this one, so this is the equation lah. Okay, the equation we get this one, Vm, okay, Vm is the voltage amplitude divided by 2 or Vpeak divided by 2 lah. Okay, so this is on the electric in the electrical lah. So Vpeak divided by 2. Okay, for calculate the RMS. So next we go for the 5 principal meter movement used in the AC instrument. Alright, so that I mentioned to you, first we have the electrodynamometer. Okay, so this one you just know what is the 5 principal movement lah. So the principal no need to apa? You can read lah, you can read by yourself. So this one you have to know what is the meter movement for the AC instrument lah. First, we use the electrodynamometer. Okay, so this you can see this one. So I think I'm not sure in FK also we don't have this one. We don't have the electrodynamometer. I'm sure. So also FK people also not have the electrodynamometer. So this is I think all version lah. Okay, that's why still. But we have to know lah the 5 principle on the meter movement on the AC. So one of the AC meter movement is the electrodynamometer lah. Okay, you can see this one. So this is how to measure the AC lah. To measure the AC. Okay, AC current or AC voltage. Okay. Okay, so second one is the iron vane. Okay, iron vane. Alright. So this one also we can use measure voltage. Okay, AC voltage. Right, you can see this one. So in category applications such as automobile, they use this one. Okay, and then number 3 is the electrostatics. Okay, electrostatic measure of high voltage when very little current can be supplied by the circuit being measured. Okay, so another one is the electrostatics. Okay, number 4 is the thermocouple. Okay, thermocouple measure the of radio frequency as a signal. Actually, the thermocouple used for measure the temperature, the temperature. And then last one is the D-ensembles, okay, or permanent magnet moving coil. Okay, this is similar like DC, DC meter. Okay, so you can see this one most widely used meter movement for measuring direct current or voltage and resistance. So normally before this on our DC meter we use this one, D-ensembles. Okay. Also, on this chapter, we discovered this same D-ensemble meter movement can measure the alternating current or measure the voltage. Okay, so for the AC also we can use the PMMC lah. Okay, permanent magnet moving coil or the ensembles. Okay, meter, right? So to measure the AC and AC current and AC voltage. Okay, but okay, you can see this one. Okay, cannot directly measure. Okay, actually, if you use the D-ensemble, we cannot directly measure the alternating current using the D-ensemble. So we have to put the rectifier. Okay, we have to put. That means we have to use the rectifier, the alternating current. Okay, that mentioned to you the rectifier. That means to convert from AC to DC lah. Okay, by use the diode rectifier to produce the unidirectional current flow lah. That means the function of rectifier here to convert from AC, okay, AC supply to the DC lah. That is a function of the rectifier, okay. For using the DR solver to measure the direct current that I mentioned to you, so they put some rectifier, so here you use the diode rectifier lah. Okay, this means this diode rectifier to convert from AC to DC. Okay, this one alright, so this is concept lah. Alright, so conversion of AC to DC okay, for example, this is our supply. Alright, so our supply is 240 that I mentioned to you. If we put 240, that's why you have to remember. So this is 240 is the RMS. Okay, this is RMS value lah. Okay, so the 10B sine wave supply gives 0 DC component, purely sine wave. Alright, so that's why we have to put rectifier circuit here, diode diode. We can put diode rectifier here. Okay, this one we call the diode this is diode symbol. Okay, D is the diode rectifier. Okay, you can see how the diode works. Okay, so it cancel out this negative. Okay, you can see this one so this is from our 240 AC. All right, so yeah, this one then be supply and then go for the diode. Okay, rectifier diode here, so automatically we cancel on the negative. Okay, on the negative cycle here, so to be like this lah. Okay, to be like this. Okay, so you can see this one Alright, so this is a symbol of our sinusoidal, okay, from TMB. So and then it will be rectified lah. That means the negative sign here, negative wave here will be cancelled out. So that's why our output for rectifier here, we measure this one. So we get like this lah. Okay, and then this is formula this formula to calculate the RMS value. Okay, so the RMS value equals to V peak divided by 2. Okay, or VDC equals to V peak divided by pi. Okay, this is formula you have to remember lah. Okay, for calculate the VRMS and VDC lah. Okay. Okay, maybe you can for example our V peak. Okay, we just give an example. Okay, our V peak is 300. Okay, 300 for example So automatically 300 divided by 2, we got the 150 150 RMS. Okay, and then to calculate the VDC. So VDC, we know V peak is the 300 divided by pi lah. Divided by pi. Okay, for example, we have calculator, we can calculate 300 divide by pi. Okay, around 95. Okay, 95 volt DC. Okay, for example, to calculate the DC voltage in DC. That is formula that you have to remember lah. Okay, actually it come from this one lah. Okay, derivation So you can see this one, the voltage average. Okay, from integration from pi to 0. Okay, pi is that 100. Okay, 180. Alright, so VM here. Okay, sine wave lah. This is our sine wave signal. Alright, so and then we integrate, we get like this lah. Okay, so the formula to calculate this one to calculate the the current, output current will be like this. This standard formula. Okay, standard formula lah. Okay, current to calculate the output current will be equal to V naught divided by R. Okay, so this is V naught 0.318 come from this one come from this value lah. Okay, this means our pi minus with 0. Okay, so this is standard. Again, you have to remember lah. Okay, you have to remember 0.3118 VM divided by R. Okay. Okay, for example, we go for the next is the DR solver meter movement used with half wave rectifier. Okay, so this is similar like DC. Okay, DC meter. So we put here, we put diode here. We put diode. Okay, rectifier diodes. Okay, so this is our, for example, our supply in RMS value. Then our output will be like this. Okay. Okay, we will cancel out on the. Okay, you can see if we cancel out on the negative cycle here. Alright, so we will be positive again, and then cancel out the negative, will be positive again. So that's why our output will be like this. Okay, using the single diode here, we call the single diode here. Okay, so automatically our output when you using the oscilloscope, so our waveform will be like this lah. So it will be cancelled on the negative side. Okay, because the diode will be flow on this direction. So maybe I just refresh again. So for the diode direction will be like this. Okay, from this one to this one. So if reverse will be 0. Okay, will be 0. That's why we cancel out on the negative side lah. So this allow for the positive. Okay, for the positive cycle only. Okay, that's why we use a single diode here. Okay, so the diode can be used the copper oxide, okay, vacuum diode, semiconductor or crystal diode lah, and so on. Okay, right. So this is a half wave rectifier. This means only use one rectifier, or you can use two rectifier. Okay. Alright. So this is okay, the circuit from figure 3.1. Okay, produce approximate half sine wave across the load resistor. So the average value of this circuit is referred to as the DC voltage lah. Okay, the forward bias diode will have no effect on the operation of the circuit if we assume an ideal diode. Okay, so on the chapter 2 we study on the sensitivity of DC voltmeter. So this is formula to calculate the sensitivity 1 over current full scale. Alright. Okay, so this is sensitivity of the DC voltage on the chapter 2. Okay, so for example, when we replace 10 volt DC with 10 volt RMS, okay, the voltage across the meter moment is just have the positive half cycle of the sine wave because of the rectifying action of the diode lah. So the peak value of the 10 RMS sine wave is the V peak equals to square root of 2 multiplied by VRMS lah. Okay, so for example, VRMS is 10 volt VRMS. So calculate the V peak equals to 14.14 lah. This is some example for example, our RMS is 10 volt lah. Okay, so this is some formula to calculate calculate RMS. Actually, VRMS equals to V peak divided by the square root of 2. So that's why we can calculate the V peak lah. Okay, and then the ensemble instrument will be respond to the average, okay, DC value of the AC sine wave, where the average is this is voltage average lah. Okay, V peak over pi. Okay, V peak for example, okay, 10. This one V peak is the square root of 2 multiplied by 10. Okay, square root of 2 multiplied by 10 divided by pi. So okay, so the last voltage average is the 4.5 volts. Okay, 4.5 volt lah. This is the average, okay, DC, okay, on the DC supply lah. Okay, alright, so that's why the pointer indicate 4.5 when the 10 volt RMS sinusoidal AC with waveform is applied lah. Therefore, we can say that the 10 volt RMS voltage is equals to 4.5 volt DC lah for the full scale reflection, or in the other words, the pointer will be deflects to 45% of the full scale lah. Okay, so this means that the AC voltmeter is not as sensitive as the DC voltmeter. Okay, so in fact the AC voltmeter using the half wave rectification, okay, is only approximately 45 as the sensitive as the DC voltmeter. So the multiplier resistor would be only 45 percent of the value of the multiplier resistor for the 10 volt DC voltmeter lah. Okay, so this is formula this is formula to calculate the multiplier resistor. Okay, so this is standard formula for half wave rectifier. Okay, for the half wave rectifier, RS, okay, RS is the multiplier resistor, equals to VDC divided by IDC minus RM. Okay, this is standard formula. Okay, standard formula to calculate the RS. Okay, and then to calculate the sensitivity of the AC equals to 0.45. Okay, how we get 0.45 is before this. Okay, that means the sensitivity is less than, okay, the less than 0.45%. 45%. Okay, that's why. So for calculate the sensitivity for AC equal to 0.45 multiplied by sensitivity on the DC. Okay, on the DC. So this is formula for half wave rectifier using the half rectifier. This is standard formula. Okay, standard formula. So normally will be given for the midterms or for the final. Okay, so that, but you have to know how to use this one for the half wave rectifier. Okay, the full wave we have another formula but the standard formula, the same formula, but the constant here will be different. Okay, so now we use the absorbable meter movement, use the full wave rectifier. Okay, so that's why here is the full wave. This is why we call the full wave. That means we have 4 diode. Okay, 4 diode. Half wave, maybe we have 2 or 1. Normally we have 1 or 2 diode. Okay, if we use the full wave, we have 4 diode here lah. Okay, okay, this one we call the full diode. Okay, so for example, like actually on the DC supply, I stop sharing it. Okay, and then alright. Okay, for example, like our this is our supply. Okay, actually the first step, okay, from the 240 volt RMS. Okay, RMS. Alright, so the first step we have the, actually this is we call a DC power supply. DC power supply. Okay, first we have the transformer lah. We have transformer. Transformer. Okay, the transformer is used to step down or step up lah. Okay, for example, this case maybe we use for step down lah. Step down to 12 volt, for example. Okay, transformers. Okay, the function of transformers either to step up or step down. Step down. Okay, and then we have the rectifier. Okay, rectifier, the function is, okay, convert from this one is still in AC. AC, so this one convert 12 volt DC. All right, so that's why the function of the, okay, the rectifier is to convert from AC to DC. Then next we have the filter lah. Okay, filter to filter our 12 volt DC. Last we have the regulator lah. Regulator. Okay, this is the block diagram for the DC power supply. DC power supply, for example, like our appliance lah. So from 240 in our house, so how you can go for the 12 volt DC. Okay, so this is process that you have to remember lah. From transformer, okay, go for rectifier, go for filter, go for regulator. Okay, unit for RMS is same, voltage. Volts is same, volts. Okay, current RMS in the ammeter lah, ampere. Ampere. Alright, so that is the unit for RMS, and it's the same. Okay, RMS is the voltage. RMS is the still in the volts. Okay, in the using the, for example, using 12 volts. Okay, volts in the voltage lah. Okay, that is unit for VRMS lah. Similar like voltage, is the similar like voltage. Okay, 12 volt, 24, 240 volts. Okay, that is unit for VRMS. Alright, so let's go for the dimension 3. So next, you can see this one. This is a full wave bridge rectifier used in the AC voltmeter circuits. Okay, so for example, here we have the 10 volt RMS. Okay, go for this one full wave rectifier. And then also we have the RS. Okay, upper resistor multiplier resistor, and this is our voltmeter. Okay, similar like DC. Similar like DC, but DC we don't have this one rectifier. Okay, for AC, okay, AC we have the full wave rectifier here. So because of to convert from AC to DC, AC to DC lah. So the output here will be on the DC. Okay, this is okay, the most frequently used for the full wave rectifier is the bridge, okay, type rectifier lah. This one we call the bridge lah. Okay, actually the flow of this circuit like this. Okay, so you can see this one. So you just follow my pointer here. So the flow will be here, and then will be go here. Go here. So because of diode will be allow one direction only. So and then go for here, go for RS. Okay, you can see this one, go for upper meter. Okay, voltmeter skirts, and then go for here. All right, so go for D3. Okay, D3, and then go for this negative. Okay, negative supply here. Okay, so the circuit on the positive cycle will be flow on the D2 and D3. Okay, D2 and D3. So D1 and D4 will be not, okay, not function lah. Will be open. Okay, will be open. Okay, so this is a positive cycle lah. You can see this one. Alright, so this is actually in our circuit lah. I mentioned to you. So will be function like this actually. So this is our transformer. Okay, and then this is our rectifier lah. Okay, so how it convert. Okay, if you can see the comparison between the half wave and full wave. So if we use the full wave, okay, so the negative wave here, so will be invert to the positive. Okay, will be like this. Okay, this is we call the full wave. For half wave rectifier, so the negative cycle will be eliminated. Will be cancelled out. But for the full wave rectifier, the negative cycle will be invert to the positive. Okay, that is the difference between the half wave rectifier and full wave rectifier. Okay, so remember this one. For half wave rectifier, alright. So the negative cycle will be cancelled out. Okay, half wave cancel out. So that's why the output will be like this. Okay, no negative cycle. But for the full wave rectifier, so the negative will be invert to the positive. Okay, positive cycle lah, so will be like this. Okay, you can see this one. That the difference between the negative, the half wave rectifier and the full wave rectifier lah. Okay, on the output, you can see on the output. So for half wave, so on the negative cycle will be eliminated or cancel out, but then for full wave, so the negative will be invert to the positive. Okay, positive cycle lah. And then the output will be like this. Okay, so the formula for full wave rectifier to calculate the volt DC is equals to 2 multiplied by Vp divided by pi. Okay, and then to calculate the VRMS equals to Vp. Vp is the voltage peak lah. Okay, divide by square root of 2 lah. Okay, square root of 2. That is his formula for full wave rectifier. Okay, you can see this one. Okay, so this is derivation. Okay, so D2 and D3 conduct in the positive half cycle that I mentioned to you, and while D1 and D4 conduct in the negative half cycle. Okay, so and then you can see this one. D1 and D3 cannot be on the same time lah. Okay, similar like D2 and D4 cannot conduct in the simultaneously lah. Okay, because of direction. You can see the flow of this one. Alright, so that's why you can see the flow here. Okay, if the positive cycle, all right, so here, so will be allow for D2 will be allowed, because D1 cannot because D1 will be blocked here. That's why the function of the diode, okay, will be blocked. So that's why you can see the symbol here. So allow only the direction for D2 D2, okay. So this one also block cannot go for D4. That's why you go for RS, okay. Go for RS, okay. Go for this one meter, and then you can see this one go for D3, okay. D3, and then go for negative. Okay, that is the positive. That's why this is called positive half cycle lah. Okay, for the negative D1 and D3 lah. Okay, so this is formula. Okay, the maximum voltage across the load for the positive and negative half cycle, this formula. So this is, for example, for positive cycle, and this one for negative cycle lah. Okay, negative cycle, that is formula. Okay, and then after derivation, okay, so the total of our voltage, okay, maximum voltage is 2 peak lah, 2 peaks, okay, 2 multiplied by V peaks, okay, V peaks here. And then similar like our negative cycle, also we get the V V peak multiplied by 2 lah, okay. So this is for negative cycle, and then to calculate the voltage average, okay, equal to V naught equals to 1 over 2 pi, okay, that multiplied by 2 peak to peaks, okay, 2 multiplied Vp plus 2 multiplied by Vp lah. So this is a equation and then the last for voltage average is 0.9 VRMS, okay, 0.9. Okay, for example, for half wave 0.45, okay, 45 multiplied by VRMS. For full wave rectifier is 0.9. Okay, this is the standard come from this one lah. Okay, come from duration. So no need to this one lah, just use the formula lah. And for you, just use the formula. Okay, so to calculate the voltage average, use this formula for full wave rectifier 0.9 multiplied by VRMS. Okay, VRMS. For example, for half wave rectifier, you have to use 0.45 multiplied by VRMS. Okay, that is for half. Okay, half rectifier. Okay, full wave 0.9. Okay, so this is formula. You can see this one. Just see the formula for calculate the rectifier. Multiplier resistor. Okay, similar like I mentioned to you. Similar, the formula will be similar like half wave, but the value here will be different. For example, for half wave will be 0.45. Okay, for full wave will be 0.9 RMS. Okay, multiplied by VRMS divided by IDC minus VRM. Okay, and then for calculate the sensitivity of AC equals to 0.9 multiplied by sensitivity for DC. Okay, this is for full wave. Okay, this is formula for full wave, and then for half wave, just change this one. For half wave is 0.45. Okay, this one also 0.45. That is the difference between the half wave and full wave rectifier. So just the constant value here will be different because of this explanation. Okay. Okay, this one will skip this one. All right. Okay. Right, so let's see the difference between the half wave and full wave rectifier. You can see this one. Okay, this is an example. Okay, the comparison between the half wave rectifier and full wave rectifier. So this is the first one. The A is the half wave rectifier, and this one will be B is the full wave rectifier. Okay, you can see this one. That is different. Okay, so for half wave they use the 2. Okay, they use the 2 diode, and for the full wave they use the 4 diode. Yeah. Okay, that's the difference between the half wave rectifier and full wave rectifier. Alright, so let's go for the example. You can see for the example. Alright, so example 3.1, design voltmeter for 10 volt RMS. Okay, AC range on the circuit shown in the figure A and figure B. Determine the AC sensitivity of the both design. So you have to remember the formula for AC Okay, so okay, not right. Alright, so formula for this one, sensitivity AC equal to 0.9 as DC lah, sensitivity for DC. This one for calculate the sensitivity for AC equal to 0.45 multiplied by sensitivity DC. Okay, this is different lah, the first step. Okay, you can see this one so automatically you can use the formula. Okay, this one first you can calculate the resistor multiplier. Okay, multiplier resistor. Okay, that is formula lah that I mentioned to you 0.45 multiplied by VRMS. Okay, VRMS equal to 10. Okay, given is the 10 divide by full scale deflection is 1 ampere. Okay, here it will be given here. Okay, 1 ampere 1 ampere. This one also 1 ampere. Okay, RM is the 100 lah. Okay, minus with 100. Okay, RM given is 100 lah. So that's why multiply resistor equals to 4.4 kilo ohm. Okay, 4.4 kilo ohms, and then you can get the sensitivity lah. So this formula calculate the sensitivity of the AC equal to 0.5 multiplied by sensitivity DC. So sensitivity DC is the 1 over full scale deflection lah. Full scale current deflection is 1 ampere. So the sensitivity for AC 450 ohm per volt lah. Okay, so this is for figure 1, half wave. For full wave, you can see the full wave will be same formula, but only the constant will be different so that I mentioned to you. So only the 0.9 and 0.45. Okay, so for full wave use the 0.9, for half wave 0.45 lah. Okay, formula will be same lah, but the constant here okay will be different lah between the half wave and full wave, but the formula will be same. Okay, that's why okay use this formula so you can get the sensitivity of the AC equals to 900 ohm per volt lah. Okay, that is for full wave rectifier. Okay, so you can go for the example. Okay, example 3.2. Okay, you can see this one example 3.2, use the half wave. Okay, half wave rectifier. Diode D1 and D2 have the average forward resistance is 50 ohm. Okay, 50 ohm, and assume to have the infinite resistance in the reverse. Okay, in the reverse direction. So that means we have infinite resistance. Automatically we know this is open lah. Okay, D2 will be open. Okay, this means okay. So only D1 we have RD here. RD we have 50 ohm, and then you can see this one and assume have the infinite resistance in the reverse direction So this is D2 will be reverse in direction reverse direction. That means R2 will be infinite, will be zero lah will be zero, infinity. So this one will be open, like open circuit. Okay, D2 will be open circuit. So then you can calculate the RS. Okay, calculate the RS, calculate the AC sensitivity and DC sensitivity lah. So normally you can use the formula This one using the formula lah. Calculate the RS, calculate the AC sensitivity and DC sensitivity lah. Okay, this is for example. Okay, you can see this one Right. So first to calculate the RS, okay, you have to calculate the RT lah. Okay, you can see this one here. I mentioned to you So this RT, okay, RS, this one we have the RM. Okay, actually this RM and RH is the parallel RM here and RH, okay, resistance shine is the parallel, okay, plus with RD, okay, plus with RS. Okay, that is formula for RT lah. You can see this one Okay, that's why you can get this one RS plus RD plus parallel of R shunt and RM. Okay, and then to calculate the RS, okay, use this formula to get this formula lah. RS equal to RT minus RD plus parallel of R shunt and RM lah. Okay, so and then you can calculate the RT. So to calculate the RT, so this is formula V DC divided by IT. So 0.45 RMS, okay, divided by IT, and then use this formula IT equal to I shine plus deflection of full scale current. That's why here, Okay, this one so current here will be this one we will plus current this one and plus this one to get the current full scale here. Okay, current full scale here equals to IM plus I shine here. Okay, that's why the formula get here. So and then the total we given is 200 microampere. Okay, and then use this formula. Okay, this from substitute this formula. Okay, you can get the RT equals to 4.5 volt divided by 200 microampere. So the RT equals to 22.5 kilo ohms. Okay, and then for the RS, okay, so the RS 22.5 kilo ohms. Okay, minus. Okay, this one is the it's not 500. It's the 50. Okay, this is 50, not 500. This is 50 ohm. Okay, and then minus with 100. This is one parallel of R shine and RM. So RD equals to RD actually given 50. This one 50 ohm. This one is some mistake lah. Okay, I cannot change here because this is in PDF, so we cannot change here lah. So you have to change on your slide lah. So this one will be 50. Okay, that's why 22.5 kilo ohm minus 50 minus 100. So the answer will be 22.35 kilo ohms. Okay, that is for calculate the RS lah. And then after calculate the RS, we can calculate the AC sensitivity lah. Okay, the formula for calculate the AC sensitivity equals to, so this is another formula to calculate the AC sensitivity equals to RT divided by range. Okay, divided by range. So this is other formula for calculate the AC sensitivity. Okay, RT is equal to 22.5k kilo ohms divided by 10 volts. So the sensitivity for AC is the 2550 ohm per volts. Okay, and then to calculate the DC sensitivity is equals to 1 over IT. Okay, so this is another formula. Okay, another formula to calculate the current the DC sensitivity lah. Okay, so another one we can use the, okay, for example for 4.4 AC equals to 0.45 DC. So DC 1 over T lah. Okay, and then we can calculate the AC sensitivity or DC sensitivity lah. Okay, so for DC sensitivity is 1 over T equals to 5000 ohm per volts. Okay, that is the formula. Okay, formula to calculate the DC sensitivity lah. Alright, so next we try last example. We go for the example 3.3. Okay, this one for full wave rectifier. Okay, is shown in the circuit 3.6. Okay, have the average forward resistance of 50 ohms. Okay, 50 ohm, and then assume to have the infinite resistance in the reverse. That means if the reverse, that means the negative cycle will be 0 lah. Okay, assume have the infinite resistance. That means very big, so current will be not allowed to flow the diode. So automatically will be open open circuit lah for the negative. Okay, that means for this one 50 will be on the D1 and D3 here. Okay, sorry, D2 and D3 here. This point to this point we have the 50 ohm and the 50 ohm. So for the negative we have the 0 lah, 0 infinity. Actually infinity, this means here will be open open circuit. So current will be not flow here lah because of the resistance is the infinite. Okay, infinite resistance. That means current cannot flow here lah. Okay, current cannot flow for D2 and D4 here. Okay, and then we have to calculate the RS. Okay, then calculate the AC sensitivity and DC sensitivity lah. Okay, so also you can use the formula lah. Okay, alright, so you can use this one you can see this one. Okay, alright, so we have this one. Okay, RD2 RD2 we have 50 that you have to remember this one. We have 50. Okay, 50 ohm here. Okay, for diode this one for diode D2 plus RS. Okay, and then parallel with R shunt and RM. Okay, plus with RD3 diode 3 lah here. Okay, on this one so they mentioned to you for the positive D2 and D3. Okay, but for the reverse will be 0 lah. Will be infinite. That means will be no current flow here lah. Will be Okay, that's why our circuit will be like this. Okay, from this is our RT lah. Okay, that's why from this one we can calculate the RT. So RT RD2 plus RS plus RD3. Okay, plus with the parallel of RM. Okay, RM and R shine here. Okay, remember the formula. Okay, for this one, for calculate the resistor here in parallel, so the formula will be RM multiplied by R shine divided by RM plus R shine. So this one okay, that is formula to solve the parallel lah. Okay, using the formula for parallel resistor in parallel, RM multiplied by R shine divided by R shine plus RM. Okay, that is formula for parallel, and then plus with RS plus with RD2 and RD3. So actually RD2 and RD3 will be same lah. That's why they put here 2. Okay, RD2 and RD3 lah. That means it's the 50 This one 50. That's why the 2 multiplied by 50 lah. Okay, this is equation Okay, and then you can calculate the RT lah. So the RT equals to VDC over IT. So VDC equals to 0.9, make sure So for the full wave 0.9, for half wave 0.45. Okay, 0.9 VRMS divided by VT, and then we don't know what is the VT. We have to calculate the VT lah. VT here VT here. Okay, so VT will be current here. Okay, current shine and current RM will be plus That's why you can get small. Current full scale reflection and current shine here. Okay, current shine, current full scale reflection So that's why the current T equals to 2 milliampere. Okay, 2 milliampere. Okay. Alright, so and then we can calculate the RT. So RT 9 volts, okay, divided by 2 milliampere equals to 4.5 kilo ohms. Okay, and then we can calculate the RS. Okay, 4.5 kilo ohm minus 100 minus 250. So the resistor multiplier is the 4.15 kilo ohms. Okay, this is for RS. Okay, and then for calculate the AC sensitivity using the formula 0.9 multiplied by sensitivity for DC. Okay, so 0.9 multiplied by 1 over 1 IT. Okay, so equals to 450. Okay, or you can calculate use. That's why I mentioned to you. So we have two formula here to calculate the AC sensitivity using 0.9 multiplied by sensitivity for DC, or you can use this one RT divided by range AC. Okay, that's why the answer will be same lah. Okay, for example, for RT is the 4.5 kilo divided by 10, so the answer is 450 ohm per volt lah. Okay, that is the sensitivity for AC. Okay, and then calculate the sensitivity for DC using this formula lah. Okay, using the formula AC divided by 0.9. Okay, or you can use another formula 1 over IT. Okay, will be same formula. Okay, will be same answer lah, 500 ohm per volt, and then also using the formula also you can get the 500 ohm per volt. Okay, that is the example lah. Okay, the example for calculate the full wave rectifier, and another one before this is the half wave rectifier. So the formula almost similar. Okay, almost same, but the value here will be different. Okay, we have to remember. So for the full scale, okay, for the full wave rectifier, alright, the full wave rectifier, the value constant here will be 0.9. For the half wave rectifier, the value here is 0.45 lah. Okay, the rest is the same. Okay, the rest is the same formula. Okay, alright, class. Alright, so I will stop here. Okay, so this one will be continue on tomorrow lah. Okay, on tomorrow. So other type of AC meter movement. Alright, so any questions so far? Okay, so you can you can try on the tutorial 2, tutorial 2, because we already finished for the DC DC meters. So next week we try to discuss on the tutorial 2. So first, try first, okay? So next week maybe on the Monday we try do the tutorial for the chapter 2, okay? So that's why you have. So tomorrow we try to finish on the chapter 3, and then for the next week we try for do the tutorial 2. Okay, tutorial 2 and try to solve the tutorial 3. Okay, can? So that's why you can try first, Try. So you have another day. Try for tutorial 2 first. And then next week we will discuss on the tutorial 2. Okay. Tomorrow we try to finish on the chapter 3 lah, on the other type of the AC meter movement. For example, we have 5 types lah. So in this one, another type is the electrodynamometer. Okay. We have the ion vents, we have the thermocouples, okay. So normally that before this, discussed we use the ensemble, The ensemble, the ensemble is similar like DC meter similar like DC meter, okay. But for the AC, they put the rectifier, Either they can put the full wave rectifier or half wave rectifier, okay. Alright, class. Any question?
Sir, send notes chapter 2 dengan chapter 3 dalam group, sir. Sebab sir tak bagi lagi.
Tak bagi lagi? Oh, saya tak bagi Yang slide ke tutorial?
Yang slide.
Oh, slide. Okay, tak apa. Okay, after this saya akan bagi. Saya lupa. Saya ingatkan. Oh, betul. Sorry. Sebab saya tu saya bagi by chapter. Alright. Tak apa. After this saya akan bagi terus sampai chapter 7 lah terus. After this saya akan bagi semua. Okay. Ada soalan lain?
Sir,
attendant. Kejap attendant jangan keluar dulu. So saya save dulu attendant. Okay, sebab attendant saya boleh dapat daripada sini je, team. Okay. Alright, so saya dah download attendant. Okay, so if no question, we will see you on tomorrow. Okay, boleh
Boleh, sir.
Okay, so at the same time, cubalah try tutorial 2 So tutorial 2 on the DC meter lah. So next week we will discuss on the chapter 2. Tutorial on chapter 2. Okay, so if no question, I will stop here. So see you on the tomorrow. Okay. Alright.
Yes, sir, thank you.
Okay. Assalamualaikum warahmatullahi wabarakatuh and okay. Bye bye.
Waalaikumsalam.
Okay, thank you.
Okay. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh and good morning to all of you. Let's continue our chapter 3 for the other types of the AC meter movements. Alright, so actually on the AC meter movement, we have 5 type of the meter movement. First is the electrodynamometer. Okay, we have the electrostatics. Okay, we have the ion vent. We have the decoupled thermocouples, and another one we have the ensemble meter movement. So before this, we are study about the ensembles. So actually, the ensemble similar like you can use for the DC meter movement, DC meter to measure the voltage or measure the current, and also the ensemble can use on the AC meter movement. Okay, but we can put rectifier. Okay, we can put rectifier on our circuit. So rectifier, the function of rectifier is to convert from AC to DC lah. This means to convert from alternating current to the direct current lah. So on the rectifier, we have two types. First is the half wave rectifier, and also we have the full wave rectifier. Okay, full wave rectifier. So next, we focus on the other types of the AC meter movement. One is the electrodynamometer movement. You can see this is a diagram. Okay, this is diagram of the electrodynamometer movement, and you can see this one is the real, the real electrodynamometer. So this is an analog instrument. All version of the electrodynamometer. Okay, so on the electrodynamometer, we have the feed coil here. Okay, we have feed coil and we have the magnets. Okay, we have the magnet and also we have the poles. Okay, we have the pole of the magnet, south and north. Okay, and then we have the meter terminals. Okay, on this electrodynamometer, we have the moving coil. So the moving coil will be okay, will be attached to the pointer. Okay, attached to the pointer lah. So the moving coil will be depends on the source. Okay, on the supply lah that we measure. Okay, so it has a same basic operating principle as the ensembles meter movement, except the permanent magnet is replaced to the fixed coil lah. So for the ensemble, they use the permanent magnet, okay. But for the electrodynamometer, they use the fixed coil. So you can see this one, okay. They use the fixed coil, okay, the fixed coil, and then for the ensemble, they use the permanent magnet lah. Okay, the moving coil and pointer which attach to the coil are suspended between the connected in series with two field coil. So we call the field coil here. Okay. All right. So the two field coil and moving coil are connected in series. Okay, such that the same current flow through each coil. All right. So the current flow through the three coil is either directional, causes the magnetic field to be produced between the field coil. Okay, the same current flow through the moving coil cause it to act as the magnet exerting the force against the spring lah. All right, so this is a basic fundamental, basic concept of the how the dynamometer works. So if the current reserve, okay, the field polarity and the polarity of the moving coil reserve. Okay, so and the force continue in the same directions. Okay, due to these characteristics of the electrodynamometer movement, it can be used in the both AC and DC system to measure the current. All right, so also the dynamometer can use to measure the current for either using for AC or DC system lah. So the basic electrodynamometer is capable of handling more current than the ensemble movement lah. So the 100 milliampere is an approximately value of the maximum current without resistor. Okay, so the advantages of the electrodynamometer is to capable handling more current compared than using the ensemble movement lah. Okay, so that is the advantages of the using the electrodynamometer. Can handle more current, okay, compared than the ensembles. So the magnetic coupling between the fixed coil and the moving coil is across, and a gap that result is in the weak magnetic fields. To be sufficient, more current must flow through the coil. Okay, which means that the larger diameter wire must be used. Okay, however, the large diameter of the less resistant than a smaller diameter lah. So this causes the electrodynamometer movement to have very low sensitivity rating of the approximately 20 to 100 ohm per volt lah. So this dynamometer have the low sensitivity lah, for low sensitivity around, okay, to 20 to 100 ohm per volt, okay, for the electrodynamometer. Okay, so this is an example. All right, you can see this one example for electrodynamometer. So an electrodynamometer movement that has a full scale deflection current rating of the 10 milliampere is to be used in the voltmeter circuits. Okay, calculate the value of the multiplier for the 10 volt range if the Rm equal to 50 ohms. Okay, so this is formula to calculate the sensitivity 1 over full scale current. All right, so full scale current equal to 10 milliampere. All right, so 1 over 10 milliampere equal to 100 ohm per volt. Okay, this is for sensitivity for electrodynamometer. And then to calculate the multiplier resistor. So this is formula for multiplier resistor, S multiplied by range minus Rm. So S equal to 100, range is the 10 volt range, okay, minus with Rm. Rm is the 50. So the answer is the 950 ohms. Okay, that is for Rs. Okay, multiplier resistor. This is same formula. Okay, to calculate the sensitivity and multiplier resistor for electrodynamometer lah. Alright, so the electrodynamometer movement with the full scale deflection rating current of the 10 milliampere is to be used as the 1 milliampere. Okay, if resistance of the moving coil is the 40 ohms, what is the value of the shine? Okay, so this is formula for shine. Okay, formula for resistance shine. So resistance shine equal to current full scale current multiply by Rm divide by 1 over, sorry, this is current, current total minus with current full scale lah. So or equal to, okay, the substitute the full scale current here, okay. So cancel out, you can cancel out the full current here, the full current here. So will be Rm over N minus 1. Okay, there is another formula lah, another formula to calculate the shunt resistor. Okay, so after calculate, the shunt resistor is equal to 0.404 ohms. Okay, there is for the shunt resistor. Alright, so if the emitter in this example is connected to 1 volt, 1 ampere DC source, okay, the pointer should deflect to exactly full scale lah. So the pointer should also deflect full scale of the 1 ampere DC is replaced with the 1 ampere AC source lah. So will be same So 1 ampere DC equal to 1 AC source will be same. Okay, the most extensive application of electrodynamometer in is wattmeter, either to measure the DC or AC power lah. Okay, so the application that we can use to use for electrodynamometer is to measure the wattmeter, to measure the power, to measure the power here. So either we can use the measure the DC power or AC power lah. Okay, so the AC signal are not restricted to the sinusoidal form, so that the power developed by any AC form may be measured. Alright, so we can measure not restrictive to the sinusoidal, but we can any, okay, any AC form lah, rectangular form, okay, trapezoidal form and so on. Also can be measured using the electrodynamometer lah. So when used as the wattmeter, a feed coil in series with the loads and therefore conduct the same current as the load lah. So plus a small current through the moving coil. Okay, so the moving coil is connected as the voltmeter across the load, where the resistor Rs, okay, is the multiplier for the voltage sensitive meter. Okay. Alright, so this is a formula to calculate the angular deflection of the pointer. Okay, theta m here. Theta m equals to km I, okay, ei, alright, cos theta. Alright, so this is formula lah to calculate the angular deflection of the pointer lah. So km is equals to instrument constant, degree per watt, okay, unit, okay, for km is the degree per watt normally given, okay, and then E is the RMS value of the source current, and then cos theta is the power factor, okay, the power factor. Okay, so because of the inherent accuracy of the electrodynamometer movement, it is used in the standard instrument, those used in the calibration of other meters lah. So because of the one another advantages of the dynamometer is the accuracy, okay, the accuracy. That's why we can use this electrodynamometer to make as the standard measurement to measure other instrument, okay, other instrument. So for example, before this, the standard instrument we use the digital multimeter, because of the electrodynamometer is more accuracy, okay, but they have a range. I will explain after this. Have the range, okay, for the frequency range, okay. That this electrodynamometer also can use as a standard instrument to measure other meters, okay, to calibrate. Okay, you want to calibrate other, for example, DC meter, okay, AC meter. So also you can use the electrodynamometer. Instead, we use the digital multimeter. Okay. So the term transfer instrument is applied to the instrument that may be calibrated with the DC source and then used without modification to measure alternating current. So they give us a direct means of equating AC and DC measurement of the voltage and current. Okay, so the most electrodynamometer movement are accurate over the frequency range from 0 to 125 Hz. Okay, that's why I mentioned to you. So another advantages of the electrodynamometer movement is the accuracy. Okay, the accuracy lah. So but in the certain range of the frequency, from 0 to 125 Hz. Okay. So on the range, this frequency range, so the electrodynamic movement are accurate lah. So that's why I mentioned to you here, it can use also has the standard instrument to measure other instrument lah. For example, we want to calibrate other instrument, we can use the electrodynamometer as the standard instrument lah, to compare with the meter that we want to calibrate. Okay. Okay, so next is the ion band meter movement lah. Alright, so you can see this one, this one on the top view. Okay, top view. So this one on the side view lah. Okay, so you can see on the top view we have the moving coil here. Okay, this is like moving coil. So this moving coil attached with the rotator. That means attached to the pointer lah. Attached to the pointer. Alright. And actually on the pointer we have spring. Also we have the spring lah. Okay, and then another one we have the fixed band. Fixed, this is fixed, not moving lah. So this one will be moving on similar with our rotator. So moving attached with the pointer here, and then we have the coil. So this is coil. So you can see on the side view, this is coil lah. Okay, inside the okay, it will be on the fixed vanes. Okay, fixed vanes here. Okay, so you can see this one, the magnetic repulsion causes moving vane to the turns. Okay, right. So this is the meter terminal. Okay, we can see this one. We have the spring, right. So this one of the moving vane inside this one moving vane, and this one will be fixed vane. Okay, so this one for ion vane meter movement. Okay, so the concept, how it works. So the moving ion band movement, okay, as shown in the figure before this, figure 3.8, can be used to measure both AC current or AC voltage. That means the ion band can use to measure the AC current or AC voltage lah. By changing the meter scale calibration, the movement, okay, the ion band movement can be used to measure the DC current and voltage. Also, the ion band can be used to measure the DC lah, either AC DC current or DC voltage by changing the meter scale calibration. By changing this meter scale, we can also measure the DC current or DC voltage. Okay, so the moving ion band meter operate on the principle of the magnetic repulsion between the poles. Okay, between light poles. Okay, that I mentioned to you how the ion band meter operate. So they use the concept of principle of magnetic repulsion, okay, between light poles. The measure current flow through the field coil, which produce a magnetic field proportional to the magnetic magnitude of the current. Okay, suspended in this field two ion band attached to the pointer lah. So the mentioned there, two ion band. One is the fixed, another one is the movable bands. Okay. So the two ion band consists of one fixed and another one is the movable. So the movable will be attached to the pointer. Alright, so the magnetic field produced by the current flow magnetize the two ion vanes with the same polarity regardless of the direction of the current through the coil. Since light pole repels one another, so the moving ion vane pulls away from the fixed vane and move the meter pointer. So this motion exerts the force against a spring. So the distance the moving ion vane will travels against the spring depends on the strength of the magnetic fields. So the strength of the magnetic fields depends on the magnitude of the current flow lah. Okay. So as stated previously, the type of meter movement may also be used to measure the voltage. Okay, so when this type of movement is used to measure the voltage, so the field coil consists of many turns of fine wire used to generate a strong magnetic fields with only a small current flow. Okay, that is how it works lah. Okay, for ion band. Alright, so the basic ion band movement has a square law response, but the fixed coil can be designed to provide a relatively linear response. Okay, although the ion band movement is responsive to the direct current, the hysteresis or magnetic lags in the ion band causes irrepressible error. So Therefore, moving vein instrument for measuring direct current are rarely used except for the very unexpensive indicators such as a discharge and charge, okay, or charge discharge indicator on the automobile. So the application used for ion vein normally we use for the automobile lah. Okay, for an AC application, so the magnetic lag present no problems. Okay, therefore the ion vein meter movement are used intensively in industry for measuring the alternating current when the error on the order of 5% to 10% are acceptable lah. So another application for the ion vein they use for extensively used in the industry lah for measuring the AC current. Okay, but the error of on the order of 5% to 10% error still is acceptable lah. Okay, that we use on the industry to measure the AC current. Okay, alternating current. Okay, so the basic current responding ion vein meter movement can be used to measure the voltage by adding the multiplier resistor as the diastolic movement lah. Okay, so also we can use ion vein to measure the voltage by adding this RS multiplier resistor similar like the ensemble movement lah. So it is very sensitive to the frequency change, can be expected to provide accurate reading over the limited range, limited frequency range, approximately 25 to 125 hertz. Okay, so also this ion vein can use to measure the voltage by add the RS, okay, multiplier resistor, similar like the ensemble movement lah. Okay, and then also the provide accurate reading but this on the limited frequency range from 25 to 125 hertz. Okay, that's all for ion vein lah. All right. Okay, so that's all for the chapter 3. So we'll recover for the chapter 3. So next you can try the tutorial 3, okay, on the AC meter lah. Okay, so that's all for today. All right, so thank you very much. Okay, Assalamualaikum warahmatullahi wabarakatuh.